On October 3, 1983, in the geological archives of the Sorbonne, a materials scientist named Dr. Elise Moreau examined stone samples from Notre Dame's crypt. Fluorescent bulbs hummed overhead. The air smelled of rock dust and chemical preservatives. She was documenting stone composition for a structural stability survey. Routine work cataloging materials used in cathedral construction across different periods. The crypt floor samples were basalt, dense, dark, crystalline basalt, transported from volcanic deposits hundreds of kilometers from Paris. This was unexpected. Cathedral crypts typically used local limestone, the same material as the main structure. Limestone was abundant, easily quarried, economical. Basalt required extraordinary effort. Quarrying from distant volcanic regions, transporting massive blocks across medieval France, installing stones significantly harder and more difficult to work than limestone. Someone had chosen basalt deliberately, at enormous expense, for a space few would ever see. Moreau tested the basalt's physical properties. Her analysis showed crystalline structure with oriented columnar formation, piezoelectric coefficient 2.3 picocoulombs per Newton, significantly higher than limestone, 0.8 picocoulombs per Newton. Acoustic impedance, 17 times 10 to the 6th kilograms per square meter second versus limestone's 8 times 10 to the 6th. Sound velocity through material, 5,800 meters per second versus limestone's 3,500 meters per second. The basalt responded to mechanical stress, including sound waves, by generating measurable electrical charge. It transmitted sound at nearly twice the velocity of limestone. It created acoustic impedance that would reflect and amplify specific frequencies. These weren't properties needed for structural support. They were properties needed for acoustic electromagnetic functionality. Moreau's report, dated November 1983, noted the selection of basalt for crypt construction suggests priorities beyond structural considerations. The material's piezoelectric and acoustic properties indicate possible functional applications in cathedral sound and electromagnetic environments. The Geological Survey Committee's response: material selection likely reflects availability during construction period. Functional interpretations speculative. Report to focus on structural analysis only. The basalt samples remained in Sorbonne archives. The crypt functionality analysis was removed from the published survey. History remembers progress, but forgets what it replaced. By the winter of 1247, according to construction records discovered in Chartres archives, crypt specifications had become extraordinarily precise about stone selection. Snow drifted past the cathedral building site as master masons received instructions. Crypte à construire en basalte volcanique. Pierre à être choisie pour résonance et réponse à son. Crypt to be constructed in volcanic basalt. Stone to be chosen for resonance and response to sound. The specifications detailed selection criteria. Basalt columns showing hexagonal crystalline formation. Density minimum 2.9 grams per cubic centimeter. Response to percussion test. Clear ring at frequency 128 Hz minimum. Blocks to be positioned with columnar axes vertical, aligned with cathedral acoustic geometry. Positioned with columnar axes vertical. Basalt's natural columnar structure, formed during volcanic cooling, had to be oriented specifically, aligned with the building's acoustic design. On a cold morning in March 1253, a stone-cutter's letter described the procurement process. Frost coated the Loire Valley where basalt deposits were found. The letter, held at the Bibliothèque Nationale, stated, "We test each basalt block by striking it with a bronze rod. The stone must sing at the specified frequency. Blocks that produce incorrect tones are rejected. Approximately 1 in 3 fails this test. Only blocks demonstrating proper acoustic response are transported to the cathedral site. 1 in 3 rejected. The acoustic testing was rigorous enough to discard 30% of quarried stone. Someone valued the acoustic properties enough to accept that waste. Shadows lengthened across 14th century crypts as evidence accumulated of sophisticated acoustic engineering. A maintenance document from 1334 described crypt acoustic characteristics. The floor, being of basalt, resonates with cathedral bells and organ performance. The stone floor vibrates measurably, creating subtle tremor perceptible to those standing within the crypt. The vibration is strongest at specific frequencies, those matching the cathedral's architectural resonance. The basalt floor vibrated. The entire crypt became a resonant surface, responding to sound from above, creating kinetic effects that people could feel. Heat shimmered above Paris in the summer of 1678, when a natural philosopher measured these vibrations during organ performance. His observations, preserved in Académie des Sciences archives, recorded, "Standing within Notre Dame crypt during Mass, I detect oscillation of the floor beneath my feet. Using a suspended pendulum, I measure the oscillation amplitude, approximately 0.3 millimeters at frequency of 64 Hz during organ pedal notes. The basalt floor responds selectively. Certain notes produce strong vibration, others minimal effect. 0.3 millimeters at 64 Hz. Measurable mechanical vibration of the entire floor, frequency selective, correlated with musical performance. The basalt wasn't just supporting the structure, it was vibrating with it. Coal smoke drifted through London in 1842 when an engineer examining Westminster Abbey's crypt discovered something unexpected beneath the basalt floor. Workers removing a damaged section found a shallow cavity, approximately 30 centimeters deep, between the basalt floor and the foundation beneath. An air gap. The basalt floor wasn't laid directly on bedrock. It was suspended above a cavity, allowing it to vibrate more freely, enhancing its acoustic response. The engineer's report described, the cavity serves no apparent structural function. Indeed, it reduces the floor's load-bearing capacity. The cavity appears designed to allow the basalt floor to function as a diaphragm, vibrating in response to sound pressure from the cathedral above. Rain fell in slow drops on a morning in 1867 when a physicist in Cologne measured electrical potentials in cathedral crypts during bell performances. His findings, recorded in laboratory notebooks, when bells ring at 128 Hz, electrical potential measured on basalt, floor surface increases to 0.4 volts above ambient. At 256 Hz, potential reaches 0.7 volts. The effect is consistent and repeatable. The basalt, when subjected to acoustic vibration, generates measurable electrical charge through piezoelectric effect. 0.7 volts generated by sound vibration. The basalt floor wasn't just responding mechanically. It was converting acoustic energy into electrical energy, creating measurable fields in the crypt whenever sound occurred in the cathedral above. frost-coated metal in January 1889, when measurements revealed that crypt electrical fields correlated with reported physiological effects. A physician's clinical notes documented patients spending time in Notre Dame crypt during organ performances report sensation of vibration throughout body, reduced pain perception, elevated mood persisting hours after exposure. Effects strongest when standing barefoot on basalt floor. Standing barefoot. Direct contact with the vibrating charge-generating basalt surface produced measurable human responses. The physician measured bioelectrical changes. Subjects on basalt floor during acoustic exposure show increased galvanic skin response, elevated peripheral circulation, enhanced parasympathetic nervous system activity. Effects require both acoustic input and basalt contact. Standing on wooden platform eliminates response. The combination mattered. Sound vibrating the basalt. Basalt generating electrical charge affecting human physiology through direct contact. By 1903, documentation of basalt crypt acoustics had become fragmented. Dust moved through lamplight as researchers found scattered references, construction contracts specifying volcanic basalt, selection criteria requiring acoustic testing, installation instructions demanding columnar orientation, maintenance notes describing floor vibration, but no consolidated understanding of the integrated acoustic electromagnetic physiological system. The knowledge had dispersed into isolated technical details that seemed curious but purposeless. Heat pressed against Paris in 1924 when Notre Dame's crypt underwent renovation. The work included installing a concrete subfloor for improved structural stability. The concrete was poured directly onto the foundation, filling the 30-centimeter cavity that had allowed the basalt floor to vibrate freely. The basalt remained, but it was now rigidly coupled to the foundation beneath, unable to move, its acoustic response capability eliminated. The renovation report stated, concrete subfloor enhances load capacity and prevents floor movement, improving structural safety. The report didn't mention that preventing floor movement eliminated 7 centuries of acoustic function. Shadows crossed 1947 Paris as a maintenance worker noticed the crypt felt different. His journal noted, the floor no longer trembles during organ performance as old records describe. The space feels dead. Sound from above no longer seems to reach the crypt with the vitality I recall from before the renovation. Dead. The acoustic connection between cathedral and crypt, maintained for 700 years, had been severed by concrete that prevented vibration. By 1967, almost no one remembered why crypts used basalt. An architectural historian examining crypt construction found references to volcanic stone and interpreted them as indicating prestige material selection. Imported basalt demonstrating cathedral wealth and commitment to quality. Prestige, the elaborate acoustic testing, the columnar orientation requirements, the suspended installation, all reduced to status symbol. Rain fell through modern Paris in 1989 when an engineer measuring crypt acoustics noticed the basalt floor showed minimal vibration response during testing. His report noted, current floor construction does not exhibit acoustic characteristics described in historical documents. Suspected cause, modern concrete subfloor preventing basalt movement. Suspected cause. The engineer recognized the problem but lacked historical context. didn't know the suspension cavity had been deliberately created. That vibration was intentional function rather than structural flaw. Frost-coated laboratories in 2003 when researchers tested basalt samples from Cathedral crypts. Their analysis confirmed basalt exhibits piezoelectric coefficient 2 to 3 times higher than limestone. Crystalline columnar structure creates directional acoustic properties. Sound transmission velocity varies with orientation relative to columns. Material selection appears optimized for acoustic electromagnetic interaction. Optimized for acoustic electromagnetic interaction. Modern science verifying what medieval contracts had specified. The basalt was chosen and oriented for its response to sound. Heat shimmered above Paris in April 2019 as fire damaged Notre Dame. The crypt, beneath stone vaulting, survived intact. The basalt floor remained, cemented onto its concrete base, structurally sound but acoustically inert. Post-fire restoration planning examined crypt conditions. The assessment: basalt floor in excellent condition, requiring no intervention. No one suggested removing the concrete subfloor, restoring the suspension cavity, returning acoustic function to the space. The basalt would remain beautiful, ancient, properly maintained, and completely unable to fulfill its original purpose. If history is written by survivors, who erased the rest? Today, cathedral crypts throughout Europe retain their basalt floors: Notre Dame, Chartres, Cologne, Westminster. The dark volcanic stone remains visible, its hexagonal columnar structure apparent to observers, its installation representing enormous medieval effort and expense. Tourists walk across these floors, their feet on stone transported hundreds of kilometers, tested acoustically, oriented precisely, installed with deliberate suspension for acoustic response. Almost none know the basalt was chosen for its piezoelectric properties. Almost none know the floors were tested to verify they rang at specific frequencies. Almost none know the columnar structure was oriented vertically for optimal acoustic transmission. Almost none know a cavity once existed beneath the floor, allowing it to vibrate freely. Almost none know the floors generated measurable electrical charge when cathedral sound vibrated them. Almost none know people standing barefoot on vibrating basalt experienced physiological effects measurably different from standing on other materials. The evidence survives. The 1,247 specifications requiring basalt, chosen for resonance and response to sound. The 1,253 stone cutter's letter describing acoustic testing, rejecting 1/3 of blocks. The 1,334 maintenance document noting floor vibration during performances. The 1,678 measurements of 0.3 millimeters oscillation at 64 Hertz. The 1,842 Westminster discovery of suspension cavity. The 1867 electrical potential measurements reaching 0.7 volts. The 1889 physician's documentation of physiological effects requiring basalt contact. The 2003 analysis confirming piezoelectric optimization. What survives less clearly is integrated understanding. The crypts used basalt. This is visible, preserved in every cathedral. But they also used it for acoustic vibration, for piezoelectric charge generation, for creating kinetic sound environments where mechanical movement and electrical fields and human physiology intersected, where standing on the floor during cathedral performance meant experiencing vibration through feet, electrical fields through body, acoustic energy converted to kinetic and electromagnetic effects through precisely selected and specifically oriented volcanic stone. They were acoustic, kinetic, electromagnetic chambers beneath cathedrals, their floors functioning as vibrating diaphragms generating charge when cathedral sound activated them. Their basalt chosen and tested and oriented and suspended for this integrated purpose. The 1924 concrete eliminated the suspension. The vibrations stopped. The charge generation ceased. The kinetic electromagnetic environment vanished, replaced by static floor, structurally improved, acoustically dead. Modern crypts retain the basalt, maintaining historical authenticity of appearance while having eliminated historical authenticity of function, preserving the material while destroying the mechanism, keeping the stone while removing the science. And in construction archives, in stone selection contracts, in acoustic testing procedures, in suspension cavity discoveries, in electrically measurement data, the evidence remains, accessible to anyone who wonders why medieval builders transported volcanic stone hundreds of kilometers for underground spaces, why they tested blocks acoustically and rejected 30%, why they oriented columnar structure vertically, why they suspended floors above cavities. Waiting for someone to recognize that material selection represented not prestige, but precision engineering, that basalt wasn't status symbol but functional component, that crypts weren't merely burial spaces, but acoustic electromagnetic chambers, converting cathedral sound into vibration and charge, integrating architecture with geology, with acoustics, with electromagnetics, with human physiology in ways modern restoration preserves visually while eliminating functionally. The basalt floors remain. Tourists walk across them. Guides explain the effort required to import volcanic stone, the craftsmanship evident in the installation, the historical significance of the material choice. They don't explain that the floors once vibrated, that they generated electrical charge, that they created environments measurably different from crypts floored with limestone or marble, or any material except precisely selected, acoustically tested, vertically oriented, suspended basalt. The science remains in the stone. Crystalline structure still piezoelectric, columnar formation still directionally acoustic, material properties still optimized for kinetic electromagnetic response. But the system is broken. The suspension gone, the vibration prevented, the charge generation eliminated, the function destroyed while appearance preserved, science silenced while stone maintained, ancient understanding eliminated while ancient material endures. Yes, dear listeners, our video ends here. My research will continue. Thank you for listening.